Hi everybody, welcome to another video in Math 1324, section 2.6, logarithmic functions. This is going to be a long section. First, we have to talk about inverse functions. So a function is said to be one-to-one if each range values correspond to the exactly one domain values. Right. So just a quick review. We have a function that each one in the domain corresponding to one in the range. So this one is still a function. So this is a function. However, this would not be a one-to-one function because one-to-one function requires that each one in the range corresponding to one in the domain. So this is not a one-to-one because if we have to go back, we don't know which one it goes to. So this is a function, but not one-to-one function. And when we have a one-to-one function, then the inverse of the function is formed by interchanging the dependent variable of f. We denote that inverse is f inverse. So if it is a function that is, I'll write like this, is one-to-one. So each one in the domain corresponding to one in the range, and each one in the range has one from the domain. So in that case, we can technically go backward. And that is the inverse. The inverse is going backward. And the notation for the inverse is going to be f of -1. So for example, if we have the function 1 to 2, 1 corresponding to 2, 3 to 4, and 2 to 5, then we just flip the order pair 2 and 1, 4 to 3, and 5 to 2. So that gives us an inverse function. Properties of inverse function. The domain of the function is the range of the inverse, and the range of the function is the domain of inverse. So pretty much the domain and range are interchanged. And the domain, if it is the x values, the range is y values, then x and y values are interchanged. And then we have one properties of the graph of the function and the inverse asymmetric on the line y equal to x. Now, let's look at one example here. Find the inverse of the function y equal to x squared plus 2 for x greater than or equal to 0. I think I make a typo here. Right. So first, let's look at the graph of y equal to x squared. Y equal to x squared is parabola. Y equal to x squared plus 2 is the parabola that goes 2 units up. So this is y equal to x squared plus 2. Now there's a problem with this. For this one, we have a y values of 3, for example, we corresponding to 2 values of x. So this is not a one-to-one function. So that's why this could not be, the inverse could not exist. Then we have to make some change. So that's why I draw it in pencil. Right. Now we have that. I show it like that. And first on the other side. Now, but this is only for x greater than or equal to 0. So that means we only have the one on the right half. So we do have the graph of the function. Right, so let's say this is the function x squared plus 2, where x greater than or equal to 0. So that's what we have. Now in this case, we have one x and one y. Indeed, it is the inverse. Now the focus on this section is not on the inverse, so that's why we just do one example like this. If it is coarse algebra or the class, we will focus more on the inverse aspect of things. So we just have this. Right. So now we try to find the inverse. So to find the inverse is, of course, we interchange x and y, and then we want to solve for it. So if y equal to x squared plus 2, and now we do the interchange of the domain and range, or the interchange x and y. We have x equal to y squared plus 2. Now we will solve for y. So x equal to y squared plus 2. So to get y by itself, we have x minus 2 equal to y squared. Of course, if we write y squared equal to x minus 2, right? And now we get y by itself, we take the square root. Have y equal to plus or minus square root of x minus 2. Right? Now, that's the problem. The function not supposed to be like this. So we have to choose either plus or minus. If it is either plus or minus, that could be good. So what do we choose, plus or minus? Well, if we focus on what we have earlier, we will have x greater than or equal to 0. So when we interchange x and y, the x here become the y have to be greater than or equal to 0 as well. So if that is the case, if y greater than or equal to 0, we have to choose the positive. So like that. Once again, because y is greater than or equal to 0, we want to pick positive. So this is a little bit advanced problem, but end up with this. So if we want to use the notation, proper notation, we say f to negative x equal to square of x minus 2. And the graph of this is the square root that move 2 units to the right. So this is the graph of the inverse. And we do have the properties. Here they said the graph of the function and the inverse are symmetric on the line y equal to x. So we draw the line y equal to x. And the graph symmetric on the line y equal to x. Right. So there's a lot of other things we can talk about inverse. However, what we try to focus on here is how on the inverse function, x becomes y, y becomes x, domain becomes the range becomes the domain. So pretty much we interchange everything. So that's what we need for the inverse. And that's what we need for the inverse to understand this section. Right. We continue. Logarithmic functions. The inverse of exponential function is called logarithmic function. is for b greater than 0, b not equal to 1, we write y equal to log base b of x, which is equivalent to x equal to b to the y. So what we have here is we have this form. If of x equal to b to the y, that is interchange to y equal to log base b of x. Now one important thing is when we draw things, notice that the y, the log, and the x, all of that on the same level, and the b is the subscript. So now should be familiar with interchanging this. So to interchange this, the base is still the base, the base is still the base. Equal sign is in the middle. We will interchange the y over here and the x over there. So on the log base is a subscript. The x here is called the argument of the log. The argument will be on the same level as the other one. Right? So that's how we interchange things. So let's just focus on that. If log base 2 is equal to 16, is equivalent to 2 to the 4 equal to 16. Now let's write it out. Log base 2 of 16 equal to 4. You see the equal sign will be in the middle. The 2 is the base. Now in the exponential form, the 2 will be on the normal level. Now we're swapping the 4 and the 16. The 4 is going here and the 16 goes here. And so this is called the exponential form. This is called the logarithmic form. And we can easily interchange between the two forms. Right. To interchange the two forms, the base become the base. The base in exponential form in the same level. The base on the log will be a subscript. The other two we just swap. Right. Let's change the following to exponential form. So the equal sign will stay. And the base is 2 will stay on the same sign. But now we go to the log. So the 2 is going to be the subscript. And then the 8 and the 3 will be swapped. Right, while the base here is the subscript. 17 go there, the 2 go to the other side. 25 is the base is the subscript, swapping the a and the -1. Right, so that's how we do it. Swapping is easy. Now to understand what this actually means, we say log base 2 of a, meaning 2 to what power is equal to 8. So 2 to what power is equal to 8. Answer to that question, right, that will be 3. So 2 to the third power is equal to 8. Right. So log is the watt in the sentence. Base to what powers is equal to the argument. Right. So that's what we do. Now, how to change back to logarithmic forms. Now, if we have, how to change this to, let me just write. So change the following to exponential form. Actually, I got a backward, did I? So this is in exponential form. We change that to logarithmic form. That makes sense. Now this is in logarithmic form. We will change that to exponential form. Sorry. Now, when we look at this, the a is the base. Equal sign. Exponential form, the base will be on the same level. And now we're just swapping the other two, 1/3 and 2. Same thing here. Logarithmic form, the 5 is the base, have the equal sign. And now we're swapping the other two. be just like that. Again, 5 to what power is equal to 25? Answer that question. That is the values of the log, right? So 5 to the second power is 25. So the log is the what in that sentence. Right. Let's evaluate the log. Log base 3 is equal to 27. So what's that equal to? Well, if we don't know what that's equal to, we're going to let that equal to, let's say, x. And then we swap 3 to x power. X goes here, 27 goes there. And 27 is 3 cubed. 3 times 3 times 3 is 27. Now two things are equal. The bases are equal. The exponent will be equal. So here x equal to 3. X equal to 3 meaning that we have log base 3 of 27 equal to 3. And 3 to the third power is 27. So that makes sense. Right. Now 9 to what power is equal to 27? We don't know what that is. Make that equal to x. And now we swap base of 9. We're going to swap the x on this side and the 27 on that side. And now we're trying to solve for x. Well, if we say 27 is 3 cubed, so that's good. 9, well, we can say 3 squared is 9, and then to the x power. Now, one property is that we learned from the previous section. When we have an exponent raised to another exponent, we will multiply the exponent together. So if we multiply the 2 and the x together, and then the bases are the same, so the 2x equal to 3. X equal to 3, so divide by 2 on both sides, so x equal to 3 half. Now x equal to 3 half, so that's what the log is. So the log of 9, base 9 of 27 equal to 3 half. So 9 to the 3 half is 27. The log base 4 of 1 half. That equal to x. Now, again, 4 to the x is equal to 1 half. Right now we'll solve for x. Now we say 4 is, now what we're trying to do is just like on this problem, or this problem, when we have two things that the bases are equal and the exponent will be equal, so we'll try to get them to the same base. 4 and 2, so that looks like that's 2 squared. Right, so that's good. Now we write this as 2 to the first power. So 2 squared to the x power is 1 over 2. Now this we know we can multiply the exponent together. The other one, I move that to the top, that becomes 2 to the negative 1. Once again, cross the line, move that from bottom to the top, change the sign. So we have 2x equal to negative 1. Now we solve for x. Divide by 2 on both sides. So x equal to negative 1/2. So we have log base 4 is equal to negative 1/2. Right. So what we have log base 7 equal to 1. Again, if we don't know what it is, we make that equal to x. Then we just solve for it. Swap 7 to x power is equal to 1. Now this is a little bit different than other things. We just have these properties. Anything raised to 0 power is 1. Doesn't matter what the base is. So this is equal to 1. So x has to be equal to 0. So log base 7 of 1 is equal to 0. Right. So that's how we evaluate the log base, log of summation base. Now the more important question is nice and even. We have things with the same basis. What happens if we have log base 2 to 7, for example? What if we have that? Now because if we make that equal to x, and then we swap, we have 2 to the x is equal to 7. And now we have 2 and 7, they don't have the same base. Now, so what's x equal to? Right? So that's the question. Now, of course, the answer, what's x equal to? My answer is very simple. X in that case is equal to log base 2 of 7. Right? Now, of course, that's not obvious, but there's certainly a way to solve for that later. Right. I'll just focus on more properties, logarithmic and exponential function. Right. Now properties of y equal to log base b of x when b greater than 0 and b less than not equal to 1. So there are two scenarios here. I just want to look at the graph of exponential function from the previous section. From the previous section, we have properties of exponential function is this. Now, remember, it goes through the point 0 and 1. The x-axis is the horizontal asymptote. The domain and range is that. Now, remember, we have the log and exponential function are inverse of each other, so we're going to swap everything. Put side by side here. This is the log. So instead of go through the point 0 and 1, it will go through the point 1 and 0. As you see, we're swapping everything. 0 to 1, 0 to 1, so swapping. The x-axis is the horizontal asymptote, so we switch the x to the y and the horizontal to vertical asymptote. And the domain and range. The range from 0 to infinity becomes the domain, and the domain of negative infinity to infinity becomes the range. So with that, from exponential function to logarithmic function, we just interchange. The x become the y, horizontal become vertical, domain become the range become the domain. We just interchange everything. We have the exponential, the logarithmic function. Now they have two cases here. One is the base bigger than 1. This is increasing, both of them. And when b is less than 1, it is decreasing on both of them. And the graph of exponential function and logarithmic function, since they're inverse, it will be symmetric. They will be symmetric on the line y equal to x. Right. So that denote a few things here. So here is the exponential function. And here we have the logarithmic function. That will to the point 1 and 0. And this is logarithmic function. Once again, b to the x will go like this when b is between 0 and 1. We have that. So that is the characteristic and properties of logarithmic function. Now we define two special logs. So one of which is called the natural log and the other one is common log. So the natural log is the one that has the base e. Remember, e is the natural number 2.71828 on the calculator. That is second be that division. So be that. So there's two log of that base e and logs of base 10. Now the base 10 is a common log, so we don't need to write the base 10, and the base e we're going to write as ln. Right. Now, so on the calculator, that 2 is the ln is the natural log. The log is the common log, base 10. Right. Now let's look at some properties of this. First of all, there's a typo here. We should say log of 1 is equal to 0. So, is that true? Well, if we don't know if it's true or not, we can just swap to exponential form. In that case, swap, we have b, try to write like this, give some space, b to the 0 power is equal to 1. And of course that is true. Right? Anything raised to 0 power is 1. Next, log base b is 1. Now again, if we swap, keep the base, keep the equal sign, 1 and b will be swapped. And that is also true, b to the first power itself. Next, we keep the base b, and then we swap the x here, and b to the x will be swapped to the other side. Now this is not log, this is exponential form. The base is b. If we write that as the exponential form, base b, and then we're going to swapping the x and swapping the whole thing on the other side. Of course, we have the same thing. So that confirms it. All of these properties are correct. Now, in general, that one obvious. This one, you can write that by default to the first power. And we just cancel the log base b and the base b. We just end up with 1. So this is what I'm trying to focus on here. Log base b of b to the x. To cancel the log base b, cancel that, and I put x. So if we have the exponential and log, both of them have the same base, you will cancel. That's what we have. Same thing here, if they cancel the log base b and b, we have back to x. Right, keep that in mind. Right. Now we have that properties, these properties. Now we write that in the common log and the natural log. In the common log, the base is equal to 10. So with that, it's very easy. I will just interchange all the b here by 10, and we have new properties. Right, so in that case, log instead of b is going to be base 10. But we're not going to write like base 10, right? We're going to write just log. The base 10 we don't need to write, it's by default. Right, so log 1 equal to 0. Now on the calculator, it did this. Right, now I replace the 10 here for b. I should write all the way on this side. And the log base 10 is a common log. I just wrap the log. And of course, next. Again, I'm going to wrap the base 10 here because the common log we don't need to write that. And we have this again, substitute the 10 in for b. And then the common log we don't need to write the base 10 in the log. So that is common log when b is equal to 10. The natural log, the base is equal to e. So now we replace all the b by e. So b is going to be e. Now log base e we know nobody write like that. It's not wrong to write like that, but log base e we just replace by ln like that instead of log of e base e. So that. Sorry, I should write. Next, replace e into b. Again, log of e, log base e is going to be ln. And then log of e like that. So log of e is ln. Right. So it's that. Right. Now we have all the properties of the logarithmic function. Log of a product is the sum of the log. So this is analogy to b to the m times b to the n is b to the m plus n. and the analogy divine, we change to subtract log of a quotient is equal to a difference of the logs. Right. Right. And then log to another power. We will take the exponential outside, change that to a product, and then two things are equal with the same base. The argument would be the same. Right, so we have those properties. Now, expand the following. So, so that we keep this property in mind. If we have the product, that's the sum. If we have a quotient, that's difference. And if we have the power, we can take it outside. Right. Now here, we can do quite a few things. Let's fold the page in half. For this one, that's right. This use the half of this. We will write something else over here. So first, this is a difference. So I will write that. I mean, this is a quotient, so I write that as a difference. Log base 5. We have 25x squared. Subtract log base 5 of y. Right? So, quotient turn to a difference. Now, next we have a product, we turn into a sum. And then the last step is just take out the 2. Alright, actually that's not 25, we can write 5 square. Now, log base 5 of 5. Now we take the advantage of the properties that we have here. Logs and exponential of the same base just cancel out. We're left with the exponent there. So log base 5 of 5 is just going to cancel out. And we're left with 2 plus 2 log base 5x minus log base 5 of y. Right. So that's what we have. Now, the reason I want to write the other side is you can draw even a shortcut for this. Now, just keep in mind that whatever the term will be on, because anything below here will carry the subtract, we'll have the negative sign. So we have the properties here that said, summary. So if it on the top, it will have the positive coefficient. If it at the bottom, it will carry the negative. So let me write the problem again. we do have 25 times x squared. Now we will write as follows. The 25 on the top because it's on the top, it will be positive. The x squared also on the top, it will have the positive. The y at the bottom will be negative. It will be faster if we write like that. And of course now we simplify the same way. And cancel out. Now to this one. We will do the traditional way of now divide and subtract. And then the product is the sum, right? Actually here we can do something else with this. Right, now for square root of z, what can we do with that? Well, let's look at the properties we have earlier. Power on the top, root at the bottom. So we have that. That n is the root. So if we have the square root of z, by default we can say this to the first power is the same thing as square root. We don't really need to write the 2, but that's essentially what we have. That's z to the 1/2. Right, so I write that z to the 1/2 is equivalent to square root. Right. So log a2 of x, and the product turn to a sum, right? Now if we write like that, that will be wrong. Remember, the minus sign here will affect the whole thing after that. So if we write like this, we should have the parentheses or the bracket here, because the negative affect everything after that, so affect the whole thing here. And we need to distribute negative to both terms here, and then the 1/2 exponent I can write outside. So that how we do it. Or if we do it a little bit shortcut here, we see that the square root of z on the top, it will be positive. The bottom, the x, we stay the bottom, we have the negative. And the y is also the bottom, so also negative. And square root of z we'll check out the 1/2. Right, so that's what we have. So that is called expanding. So from one big log, we turn that into a bunch of little logs. Now, we do the reverse. We call the condensing. To do that, just do this in reverse. So if we can bring the exponent outside the coefficient, we can certainly bring it back in. And now we can, so to condense them, to put them into one big log, we have to have one of each log. So one of this, one of this, one of this. In that case, we can just write that as one big log. Whatever positive we put on top, this one negative put at the bottom, and finally 1/2 power is equivalent to the square root. We don't have to write like that, but see, we can write like that. So to combine the logs into one big log, we have to have one of each log, so we can combine them. Now here we can have to have one for each log. So one for each log. Take all the coefficient inside, and now with that we can write that everything in one big log. Positive will stay on top, negative at the bottom. Right, so that is called condensing logarithm. Right. Now we go to logarithmic equation. So now we will solve for logarithmic. So let's say we have the log equal to number. Well, that's easy. Now, one thing we should focus on in every logarithmic equation is that, remember, we have the properties of the log. The domains only from 0 to infinity, only positive numbers. So we have to say that whatever we have at the base doesn't matter. This have to be positive. So when we solve for that, make sure whatever this is, it have to be positive. So in that case, we write little note for logarithmic equation. We need to check to make sure all arguments are positive. Right, so now we to solve for that. This one's different. Right, let's focus on things. That different type of equation. This we have the log equal to number. This we have the log equal to log. This we have a number by itself. So when we have a number by itself and or we don't have it, different things. If we have a number by itself and like this, we can just swap to exponential form. Right? And now we just plus 1 on both sides. So 3 to 9, whatever that is. That's a very big number. So that. And then we just plus 1 on both sides. So have x equal to 3 to the 9 plus 1. Which is that 19,683 plus 1, so will be 19,684. Right. Remember, we need to check. Log B3. Now we have 19,684. All we need to check is just make sure that inside of this is positive, and it is. So that's good. So if x equal to this. So that's good. That's what we check. Once again, if we have a log equal to number, then we swap to exponential form. Now we have different things. We have all of them have logs. So in this case, what we write is combine the log here. Addition, remember to condense, addition turn into a product. Right. So we that I will multiply them out. Now we have both of them. We have the log b3. Just going to cancel. Two logs are equal. The bases are equal. The arguments will be equal. Now we just need to solve for x. Multiply them out. X squared minus 3x equal to 10. Now subtract 10 on both sides. Now we solve for x. Just use quadratic formula here. So negative 3 plus or minus negative 3 squared minus 4 AC over 2A. So we have 3 plus or minus 3 squared is 9 minus, so that plus 40 square root of 49 over 2. So 3 plus or minus 7 over 2. 3 plus 7 over 2 is equal to 10. 10 over 2, which is 5, and 3 minus 7 over 2, negative 4 over 2, which is negative 2. So I have 5 and minus 2. So now we need to check. First, when x equal to 5, we have log b3. Now we substitute 5 for x. Find for x. Here we have positive, which is good, and that's positive, which is good. So that's all we check. We don't need to verify that they're equal. Just need to check that inside all the logs are positive. So here x equal to 5 is a solution, which is good. Now we check for negative 2. Right on the first one, we don't have to go any further because this is negative, so it failed already. So that's not a solution. So we only have one solution. It's x equal to 5. Right. So to recap, if we have log on everywhere, we try to get one on each side. A log on the left, a log on the right. The bases are the same. The argument will be the same. So that is where we have a bunch of logs everywhere. Now this one, almost except we have the numbers, so we have to do a little bit differently. So if there's a number, we have to swap to exponential form. So in that case, we still need to combine that into one big log. So this is addition. So combine that into one log. Now with that, we can swap to exponential form. One log equal to number. We swap. The basis of 4 will stay. I'll move the 2 on this side, and x plus 5, and x minus 1 here. So now we'll rewrite this. 4 squares equal to 16. Now we multiply that. X squared minus x 5 minus 5. Combine like terms. Combine like terms. 5 minus 1 is 4. Right. Now we can move everything on one side. Right. And then of course, if you want to, you can rewrite this as x squared plus 4x minus 21 equal to 0. So two sides are equal, we can just swap them. Yeah, that makes you more comfortable. Equation equal to 0. Right. Now again, quadratic equation, that should be simple. that gives us negative 4 plus or minus 2. Right, 4 squared 16, negative, so that's 16 and 4 times 21 is 84. 16 and 84, that's square root of 100, which is 10. So we have a minus 4 plus 10 divided by 2. That is 6 divided by 2 is 3. Now we have minus 14 divided by 2 is minus 7. And now we check. Now x equal to 3. So that is right. So inside every log is positive. All the arguments are positive, so we good. We have x equal to 3. Now we check. X equal negative 7. Right, we don't have to go no further because right the first one, this is negative 4 and negative, it fails. So negative 7 doesn't work, so the equation only have x equal to 3. Right, so that logarithmic equation, once again there are two types, one of which we have log equal to number, we can swap the exponential form. And if we have all the logs, we cannot swap. What we do is we make the argument to be equal each other. Now next we have the chain of bases. So for that, let's look at one easy example. In that case, what if we want to, let's say, evaluate log base 4 of 7, right? Now in old days, this calculator, the typical calculator, we only have the log base 10 and ln. So how do we evaluate something like this? Well, in that case, we can use this chain of bases formula. We can use any base. So in that case, if we use log base 10 or use log base e, the natural log, I prefer to just use the ln. So in that case, we can write this as ln. So the log base of 4 now change to log base of e. So that's called the chain of base formula. Now, the 7 above, the 4 at the bottom. So we just have that. So to evaluate this, the rest we just use a calculator. We have ln of 7 divided by ln of 4. Now, but if you have this calculator and if you hit math and go way down to option where say log base, you can just enter exactly as we see it. of course we have the same thing, right? So either way, right? So when we have a log of different base, if your calculator cannot use the log base, you just have to use the change of base formula, and I prefer to use ln. Right. Let's look at some example here. Right, so I do this two different ways. Now before we do it, let's look at some problem that we have earlier. Right, like this. So when we have two things that have the same basis, the exponent will be the same. So just base 3, so x equal to 3. So that's easy. Now we just say that what happens if we don't have the same basis. So what when we don't have the same basis? Well, remember, we can always swap to exponential form, right? So as for this one, we swap. The base of 2. And then we swap. The 5 go there. And x plus 1 go here. And now we subtract 1 on both sides. And yeah, so that's what we have. That's it. Right. Now, so that of course that certainly works, but I just want to do it a little more systematic way, because things might get more complicated, because something like this we cannot really swap. So another way to do this is, as of course, let's rewrite the problem. And now what we do is we can check the log on both sides. Right, so we check the ln on both sides. So we can check the x plus 1. Multiply it out. Right, and now we solve for x here. So what I do is we can subtract the ln of 2 on both sides. And to get x by itself, we divide by ln of 2. Let's say, wait a minute, what? This sounds like a lot more work than that. And of course I agree. And the answer is not as nice as this, but they are the same. Of course, one way to confirm that, put that in the calculator, put that in the calculator, so get you the same thing. But another way to do this, we have ln of 5 or ln of 2. We just split this. And now ln of 2 over ln of 2 is just 1. And now if with this we can write the change of base formula, right? Let's write backward. We have log, the bottom is the base, ln of 2 over ln of 2 is 1. So in this they are the same. Right, but we can just stop here as the answer. Right, bottom line is, so when we have exponential equation where we cannot convert them to the same base, we will take ln on both sides. Of course, you can take any log of any base on both sides, but I prefer just write ln. It's more generic. So something like this. We don't know what it is. Take ln on both sides. Then we can take the exponent outside. Right. Now we solve for x, two different places. So this is slightly more complicated. So x ln of 2. Now we multiply it out. X ln of 3. X ln of 3 and then 1 plus ln of 3. Now try to solve for it. Move the x to ln of 3. Now both of them have x. I can factor it out. And now we divide that on both sides. So that's what we have. So that's what we have. Now one thing to say, for the exponential equation, this is not logarithmic equation. We don't have to check from the beginning to see if they actually the argument have to be positive. We don't have to check that. However, it's always nice that we check, put here to make sure that the both sides are equal. Sometimes we do need to check that. We don't have to check the arguments to be positive, because original problem there's no log, so there's no way to no need to check that. Right. Let's look at some application. Suppose that $1,000 is invested on the account that is compounded continuously. Find the interest rate if after 10 years the amount is $1,800. So this is continuously compound interest, which is A equal to P e to the RT. Now let's just write everything we have from the problem. Suppose $1,000 is invested. So that is the principal of $1,000. The interest rate we don't know. That's perfectly fine if we just have one variable to be solved for. After 10 years, the amount, so the future value A is 1,800. Right, so I have everything but R, which is fair game. Substitute in here. Let's see what happened. 1,800 equal to 1,000. The rate we don't know, but we do know time is 10 years. Right, so now we're trying to solve for R. So first, what we can do is if we divide by 1,000 on both sides, we get rid of that. We just get the exponential term by itself. So it's 1.8. That to the 10R. Now we try to solve for R. Now just like this equation, we try to get them to the same base, the same bases. But if we cannot do that, we have to take the ln on both sides. And now we can bring out the 10R outside. Right. Now I want to, oh, it's here. ln of A is equal to 1. So like that. Or from here we can just say it, cancel out the ln of E, cancel out here. But right, so we just say it. ln of E is equal to 1. So essentially 10R times 1 should be just 10R. And if we want to solve for R, we can divide by 10 on both sides. So R is equal to ln of 1.8 divided by 10. Now we have 0.0588 and so on. So that is 5.88%. This question does ask for rate, so that look reasonable. So that's what we have. Another example. How long does it take for an account to double its balance if it is invested on the 5% compounded annually? Right. So this is compounded annually. Compound interest. So we have that. Let's see what we have. How long does it take? So the question asks for time. And all we have is just double its balance. So that means the future values A is going to be twice the original investment. A is 2p. Future value is twice the principal. And then 5%. Annually meaning one time a year. Right, so that's what we have. Now substitute everything in here. We have A is twice the principal. Rate over 1. T, we don't know. That's perfectly fine. We solve it. Now we can divide by P on both sides. That gives you 2. P and P cancel out 1. So this is just 1.05 to the T. Now we just solve for T. That should be easy. Since we cannot get them to the same base, we can take ln on both sides. we can take the T outside. And divide by ln of 1.05. So T is equal to ln of 2 over ln of 1.05. Right, let's see. If the calculator can do fraction, just do fraction here. Ln of 2 over ln of 1.05. Oops. Have 14.2. And this is as for time, so that's in terms of years. So how long does it take for investment to double values? If it is 5% compounded annually, well, the answer is 14.2 years. Right. I said we focus on this in the next chapter as well. Next we have an application, half-life and carbon dating. So cosmic ray bombardment of atmosphere produce neutron. So that pretty much that will create carbon-14. So turn the nitrogen to carbon-14. So carbon-14 is radioactive. So that means pretty much all the living things have carbon in it, and all the living things will have carbon-14 in it. Now, the difference between the regular carbon and carbon-14 is that it is radioactive. So all the carbon-14 that in our body, over time, we change back to nitrogen, meaning it disappears. So originally, let's say I have, it is not, let's say we simple, at the moment, I have the ratio between the regular carbon and carbon-14. Let's say at the moment I have 10% of carbon-14 in the body. Right. But over time, the carbon-14 will change to something else. So maybe 1,000 years later, I only have like, I mean, of course, my bone will only have like 5% of the carbon-14. And so in that case, based on the percent of the carbon-14 in the remains, we can determine how long since it happened. So when we alive, we can consume the carbon-14 and the carbon. But when we die, we no longer consume any carbon-14. So the clock will start, and the carbon-14 will start to decay, and the percentage of carbon-14 will get smaller and smaller. And based on that, we can compute the time where the object is still alive. So in that case, we can have the equation like this. And we say that we have the percent of carbon-14 will be given by this equation. Now find the half-life of carbon-14. So the half-life here meaning that the time that takes for the carbon-14 to reduce to half of its original amount. So half-life the time that takes to reduce something to half of its original amount. Alright, so of course if it half-life carbon-14, so the time it takes for carbon-14 to reduce to half of its original amount. So just like this problem, the time it takes to double the amount of something. So this is half of original something. So this is called a radioactive decay. So it's not an increased function. So investment like this, the amount will get increasing. Something like this, the amount will be decreasing over time. So that's why the rate is negative. Right, anyway, so we have that equation. Now we have half-life, meaning that the original amount, the future values, is equal to half of the original amount. So I'm going to substitute into this equation. That cancel out. I'll check LN on both sides. And here we can bring the exponent outside. I will say this quite often. Ln of A is equal to 1. So that multiplied by 1 just cancel out. So we just have that. Now divide by this number, we have t. So with this we have t equal to ln of 0.5 divided by this. So that 5,589.9. So let's say about 506 years. So about that. So of course, just an estimate. So it's good. So that means it takes 5,589 or 5,590 years for something, for carbon-14 to reduce to half of its original amount. So if we found an object, let's say we find a piece of bone, for example, and then we calculate and we say the carbon-14 on that bone is only half of its original amount. So how do we know if it is half of its original amount? Well, we don't really know what its original amount is, but we can know at the moment for an object is alive, we can calculate how much carbon-14 is in that object, so we can use that as a reference. And so in that case, we can say how much carbon-14, the percent of carbon-14 present in that bone, and we can calculate the time. If it is half of its original amount, that means that bone is 5,590 years old. So that is called the carbon dating. Alright, so with that, we finish section 2.6. As always, thank you for watching and see you in another video in Math 1324.